In fact, let me go through the part of that. We already done some part from last time, so. New version is going to be released in October sometime.
Are?
So they have two major releases every twice every year.
But,
April and
but we're not going to update in the middle of the semester, right?
we can do that.
It'll crash things.
You install new one and then they will tell you how you upgrade the packages. So I went through part of this solution last time. Something else that I'd like to talk about today. This with part of this we can assume that. Yeah, I had created a function called FRQ. So it's supposed to be there. And the adult data set is supposed to also have this column. Run through this, you have this additional column, EDU 2, 3, and education. We have done that last time. As along with this break function, I wanted this entity. Put this on first. Yeah, we had that last time. We have seen the frequency distributions of hours per week and I mean the salary, okay, like a two group of salary, okay, according to age distribution, right? And then hours per week. And that here, this is three-way split. And see, this is probably asked. You can see that whether there's a presence of interaction, right? Between two variables. Unfortunately, either way, the labels will come together. So that's why you need to separate, even if you use LAS, because and of course there's a way to mess with that. Just have to modify their code. That's a possible way to do that. I try not to get into that either. But anyway, we have some idea that here I split this horizontally with education first. Okay. So here education split from the point this preschool and then grade school and so up to down there. Because we can use other education level as well. Right? And then within education, we split vertically by gender and then horizontally by the salary. Right? Okay. So, this allows us to see whether there's a three-way interaction. You can see the proportion table by using this command. You can see that. Okay. Table. So basically, that figure shows this kind of the distribution. To do that. You can see whether there's interaction or not by looking at what's Whisker plot. Did I talk about this last time? It's like they are kind of similar. The profile is like very similar. We can do for the other one, the distribution for hourly per week. Probably this is the case. And here is another view about box whisker plot. Okay. Model this the education. Again, the teaching on salary, so we have this sequence of distribution. So basically, here this is a result. Okay. Well, you can do this. A lot of this. Now, if you use Reto, when you explore data, there's a tab you can click. You can explore missing value. Okay. You can explore the correlation among variables having missing values. Actually, it's done by this. I'm trying to say that just go down to detail. You can just do it by yourself. Actually, well, it's nothing but just generating the indicator variables, which is whether it's missing or not. So it's not much difference. Here, let's try to explore this way. Suppose I take just original data. Okay. So here, basically, this is in the adult data. So we have seen this earlier. Let me show that again. So you can see the first 15 columns up to Sarah. These are the original data, right? So explore the original data. Suppose I have this subset here. So a subset. Okay. Just extract the first 15 columns by this. Okay. And then and just look at whichever variables having at least one incomplete cases. Okay. The function to use is called complete cases. Complete cases. Okay. That's a function to explore. So here, these are the three variables having at least one missing variable in the data set. Also here, this is not going to respond to that peculiar number we seen last time, 99,999 for that kept again. Unless if you understand that it's missing value calling, we set that to missing that. We can do that. Okay. So basically here we're looking for apply function is really a very versatile function. You can use that. Okay. Apply to a data frame, and usually of course here you have this. You have data frames that all columns are sort of same type. Okay. Of course, it doesn't have to be. Okay. Not exactly the way I did it. So I didn't do it that way. Okay. I only explore whether there's missing value. So to that, actually, I will not distinguish whether it's a vector or it's a character variables or it's a numeric. Okay. So here I use apply data. That's our data. 2 stands for column, right? So I look at per each column. Okay. So when I use 2, the function that you see the x here represent any of this column, right? So starting from column 1. Okay. So that's what you're doing apply for. Okay. So apply for first column with this function. Complete cases give you a vector of true, false. Okay. If you have missing value, then true. Otherwise, okay, false. Sorry, complete case. Sorry. If you have missing value, it would be false. Okay. So this is complete cases, right? If you have non-missing value, then let's see. Non-missing value is true, and missing value is false. That's complete cases. So kind of overwrite this. This is another function called sort of working in reverse way. Okay, it's called this SNA. So we can use that. This is another function testing whether vector elements are missing or not. So here, if I find any incomplete cases, I record that to this column. So here, income variables will contain this, right? Basically, I'm going to use this later. That's why I save it today. So I'm a little bit slow today. Okay. So here, storing these incomplete variables. And then you can also see any cases is incomplete. Because when you do this correlation of the missing values among columns, you only look at any cases contain at least one missing value. So yeah, look at all the missing cases. Okay. So we can run the complete cases for the entire data set. So look at all observation-wise. Okay. So say complete cases, and we say this exclamation means that reversing the logical true false. Okay. So basically, I give you logical true false. If you have missing value, then it's true. Okay. So this is in complete cases. Assign that in complete cases. Let me ask you, when I do sum, what does it mean? So here you have a column of true false. Okay. True for when observation contains at least one missing value across the variable, right? Is that? And false when the observation is complete. So when you do sum, what do we have? This gives you number of complete cases, right? Number of incomplete cases. So that's good. Did you actually find there are total 2,399 cases having missing value, right? Okay, so you have no problem. Okay. So here, basically, I do this step by step to show that. Okay. The reason to do this is because maybe there are some data set needs to do some spatial treatments, and you do that first, and you can run this code. That's good. So now let's subset the data set. Okay. So let's subset this data. Okay. We take our data set and only subset in the incomplete cases. We only look at observation having at least one incomplete cases over these three columns, right? These three columns having missing cases. Because we do select also. Okay. So if you ever wonder what this is, here, show the dimension anyway. So here, this is a data frame of 2,399 rows and 3 columns. Where these columns are basically these 3 variables having missing values, right? Okay. I try to make data more informative, but actually we don't need to do that because the reason I changed this because we have incomprehensible labels of the labels. Okay, we have label like FDR dash LCL dash. So I kind of changed that. This is not really needed in this case. Okay, so I just changed that labels anyway. But here, this is a command to produce a correlation among the missing variables. Okay. So basically, we apply data column-wise, and we do exclamation complete cases. If missing value, we get a value of true. Okay. If non-missing value, get a value of false. In a sense, this is column indicator, right? This is indicator vectors, right? True for 1, false for 0, right? Okay. Of course, at the end of this is the entire output is actually this entire metric is a logical vector. But anyway, when you apply correlation to that, I will treat that logical value as 1, true for 1, false for 2. So anyway, here, where are we at? Right here, okay. So run the correlations of missing value. Basically, just use indicator variables. Okay. For any columns, okay, if you have missing observation, then you give a value of 1. If you have non-missing value, give a value of 0, and then you can find the correlation among these missing value cases. Okay. can see that they are highly correlated. Yeah. Probably this give you more insight about data. Probably, and you go back and look at the data, it probably makes sense if you try to look at it, look into this. Okay? If I tabulate this, use cross tabulation, okay? Because we see that previously the work class is highly correlated with occupation, okay? And then here we do the cross tabulation of work class and occupation, and even try to report the missing value there. That's how you can see the missing value of work class is associated with missing value of the what is occupation. And that's why. Okay. That makes sense, right? This is basically what data is. When you have missing value work class, of course you have tends to have missing value in this occupation as well. So that's why you see that high correlation. The problem is this is not really helpful. Unless you can see according to this, let's look at this again. Okay. This is correlation. This is correlation among these three columns with missing value. So this is so-called the missing value correlation matrix. Okay. Actually, I use the default Pearson correlation. You can try to use Kendall or use Kendall Tau or use Spearman. They are exactly identical because of the way we have only 1 and 0. So did you see this in Redhawk? If you use Redhawk, there's a particular button when you press to produce this report on missing value. Actually, it's done this way. Okay. So let me just show you that result. Here I have in my this R course link. If you go to this R course, there's a link about this. This is the panel correlation functions I wrote. Okay. Well, actually, I kind of borrowed that from the latest package they have in the help. There's a there's help page on the latest. Okay. They also already created this so-called this panel correlation. I modified it slightly, so actually say this is the one I created. Okay, only just a slight modification of the result. Okay. So basically, this is the modification. The only modification I did is on this cutoff. The reason is that originally we'll see the result anyway. Originally they labeled this or use like reverse color, okay. And you won't be able to see that the labels when you have very near zero correlation. So I use a reverse colors on that one. The only modification I did is right here, just label it. I give to so sometimes if you use the built-in function, you made a slight modification and make it so much better. Okay. So here, if you solve this one, actually I gave the instruction on how to do this. Okay. And actually I already done that. So use the source in that. Then copy paste to your R session of these 2 lines if you have that already. Okay. So let's do this. Okay. And first of all, this the correlation matrix, the rows of correlation matrix, okay, must be arranged in a certain order. So the result, okay, the result will show is the best result. Okay. They so according to the distance, some kind of distance measure. Okay. I just take a correlation matrix, turn into a distance measure, so mean that the negative means that the negative is that you can actually see that. Okay. I forgot what I did. So turn that into a distance measured by what is that between occupation and class? And as you can see that it's negative correlation means that they are farther apart, right? Okay. Mostly similar, more distant, okay? I forgot what I did there. Anyway, let's just look at that, okay? Anyway, you do these distant measures, and here this hierarchical clustering, and which is actually a subject, this unsupervised learning that we provide in the future, okay? Hierarchical clustering, and then make them into dendrogram, and then just order them. So we don't have to need to know the details. It's just in the help documentation, okay? In some kind of order, then this chorogram or choreogram can be easily presented, because this is the graphics is here is not really nice because we've got 3 variables. Okay? In general, if you have a large number of variables, you can see a nice layout of this result. Okay? So basically, this is what it appears. Here I didn't label the result. Okay? You can put the labels on that. Okay? So basically, red color represents the negative correlation, right? The blue positive correlation. Okay, and here these are. Well, of course, if correlation is near 0, then you expect a lighter color and also with a round shape. Okay. And with a stronger correlation, you see a more elongated ellipsis. So so basically this idea. Okay. And actually, you can see internally there was a one. Actually, there was a function. Actually, there's a package we actually call in that the joint ellipsis. So we don't have to know the detail.
If it had greater amount of data in it, how would the ellipses change? Would it be fatter or?
Yeah, if you have I have another example later. So
Okay.
we have very sort of near 0 correlation. You can see. If you have correlation near 0 base, you see a round shape. Okay. Because of this along these diagonals, they arrange this will be the correlation of any variable with itself. So that's always 1. Right? So, and what I did is here I kind of can label this result. So here you can actually turn this off. Okay, I'm commenting that and see the result. Did you see that? Did you see this in what is that in Reno? Here, basically, here I also label this result. Okay. So still, this is not really good, not a major improvement because with a very large correlation, actually near plus minus 1, you actually shouldn't use a white color to label. That's what I use there. Okay. Probably not a good idea. Maybe I need to use an outline font so to outline this character so much easier to see. But anyway, this choreogram basically label the correlations. Okay, this is so. The number shown here is correlation times 100, so that's why I see negative 96, right? So that's negative 0.96. You want to see the labels of that result. Here I use a date too, so that no wonder I put this in between. Okay. In package CARET, there is a way to evaluate the importance of the variables. Okay. Either it's model-free method or just a model-dependent method. Okay. Model-dependent, the model could be the tree model, it could be like this linear discriminant analysis model, and so on, a whole lot of different models. Okay. to evaluate variance importance. And here at the moment, here we didn't build any model, right? So this is model-free variance importance. And this has some feeling about the variables. Okay? So here we require this package. Require this package first, okay? And then here this command filter variance important basically allows you to let me run it first. It takes a while, maybe 1 minute to do this. Oops. So I created data too. Oh, I didn't do data. I need to do this first. Okay. Day 2 need to be first created. It's running. It takes a little bit of time to run that. Usually it's probably 1 to 2 minutes to execute this. Okay. It's a little bit more computation time on evaluating the importance of the variables. Okay. So importance of variable is measured against our response variable here. So here, this is our response variable, right? Okay. This is our adult data set. Okay. I might as well just use DAD2 here. I'm supposed to change that more consistent. But actually, that's an identical result. Okay. And here we have subset date 2 and select equal minus salary. So all by this target variable. We're supposed to do that, right? If we change that to DAT2, actually the result will be identical. We're supposed to do that. The first argument to this filter variance important is the entire sets of feature vectors, right? It means that that's the input variable. So, okay. So we have everything but salary, right? We move in that columns. Okay? So here, this is our subset of data frame. Okay, and the second component would be the target variable. Okay, not in the data frame form, just in the vector form. Okay? So corresponding to that, our response variable. Okay? And you fill it out with this, and the result is a 13 row and 2 column data frame because after removing salary, this day 2 originally has like 14 columns, including the target variable. It's 14 columns. Because I already removed this thing here, right? Okay, I removed this education number, and EDU2 and EDU3. We do have another column. What is that? Another column is called education, so we remove that. And if the variance important, you can see this dimension. Okay. There are 13 rows and 2 columns. The reason why it's 2 columns because we have 2 classes. Right? You can actually see this result. Okay. The reason why you see this is because the column names has to comply with the naming criteria. That's why they changed that. They changed this less equal sign to 2 dots and less signs to that automatically. Anyway, I think probably there's another argument that allow you to space write these different levels. I didn't take a look about this function. We have something like that. Okay. So we have this variance importance measurement evaluated. It's 13 rows and 2 columns data frame. Okay. So basically, okay, 1 column is for the variance importance for that particular classes. Okay. In general, they may not be completely identical. Okay. If you rank in order of importance. Okay. Probably there's a slight trail, or sometimes the importance will be different. But it just turns out that in this case, in both 2 classes, the variance importance are in the same order. Okay. Let me show you that. Okay. Now here, this is just for the programming part. You really have like more classes. You can do this very similar programming. You can get the same result. So that's why I try to do this way. Okay, show more programming on that. Yeah. The reason I want to plot the variance importance of each class separately, and then So each one is a part, and then later on I just assemble these two together. So that's why I need some kind of arguments here. Okay? Just has more figures to come on the same page. So that's why I use that. Okay? And just let me just run through this. For each class, this would be the variance importance part for that result. Okay? In general, the variance importance may not appear in the same folders. Okay? Probably slightly off. Here, it just happened. Okay, they are sort of identical. Is it a surprise that relationship comes first? Okay, almost identical to education. Also, that variance importance. Maybe somewhat this relationship is also highly correlated with other variables, except that this is categorical. So you got to find a way to find the correlation. Right? You can use like Spearman correlation. So here you can see if, and as you expect, this final weight comes last, right? At the variance importance. So here we have these two separate kinds of variance importance. Okay, evaluated. It's done by this Craven dot William Craven. So this is something that actually created. So this could be just a reference for your various variable selection. I'm not saying this is the result is not absolute, okay? Because this is model free. So do you try that? Of course, if you look at the help document, this vignette of this carrier package, they also talk about near zero variables and this and also spin out the highly correlated variables. Right? You can also see that. Actually, earlier we showed the correlation, the missing value correlation matrix. You can see all the entries are highly correlated. So imputation, you cannot impute one variable alone, right? You should take into consideration all the missing value. If you want to replace missing value by others. Okay? And actually, there are algorithms actually look into the imputation of missing value, like a tree model will do that. Our part is the package we're going to look at. Okay, it's also take into the information that of other variables and then try to impute the missing value and then build the model. So sometimes it's really important to look at this correlation matrix. Okay. See, surprisingly, the correlation among the 5 quantitative predictors are very small. Look at this one. So here I run correlation. Here I run correlation of our data. Do I have day 2 already? Okay. We already have day 2, right? For this data too, I run correlation among those numeric variables. Okay. I take in numerical variables only. So here, this is S applied to data 2, okay, because it's a data frame, XORs, okay. So we take each column and give a true false whether it's a numeric columns or not. Okay? And then we can use this to subset columns. Okay? So I use this to subset column, only numeric columns will be subsetted, and then we run the correlation among these columns and use a pairwise complete cases. Okay? By default, I think the default is that only look at the complete cases. So suppose you want to look at pairwise complete cases. Okay. So look at each every pair of 2 variables and look at and only extract the complete cases and run the correlation. Right? So basically that's what this does. Okay. I'm surprised that these correlations are so small. Probably there's other explanation. Remember last time we talked about this capital gain and capital loss. We have a huge amount of zeros, right? Maybe that should be okay. exclude it before we do calculations of correlation. Maybe we should do that, right? And also there's a whole bunch of this 99,999. We don't know the meaning of that, okay? Maybe there's a way to deal with that. If that is missing value, of course we can exclude that. If that is so some right sensor data, we can find a way how we deal with the correlation of right sensor data. Okay, so anyway, let's not modify it. If you are interested, just looking at them, maybe you should just do further. But let's just take as is, and generate this parallelogram again by doing this. Yeah, take this the second correlation matrix here. Let's run this level. Let's run level plot. Okay. So now this is what this probably answer your question. See more round shape here. Okay. The original function would label this with reverse color, means white color, using background color. So you won't be able to see that. Okay. That's why I modified a little bit. Okay. I modified to let it show. Maybe I should use a different font for that, and everything will show. Okay. Anyway, we don't have to worry about this. Okay. So here, this is parallelogram among these quantitative variables. Okay. Maybe this is one way of indicative of, say, maybe you want to exclude some variables. Some variable may be okay, linear correlated with the combination of other variables. But here, of course, we only look at the pairwise correlation. Okay. If you have two sets of variables, one look at their correlation. There is a method called canonical correlation. You can look at that. I'm not getting into this. Okay, so I hope that at least this will be helpful for your this one. So maybe I should ask you this question again. Do you feel comfortable to submit case study number 2 next Tuesday? Sound iffy. So we postponed the first case study. Should we also do that for the second study? Yeah, I should. And then probably at the same time I should assign the third case study before we know it. Okay. Okay, so here this is parallelogram of this. All these variables are maybe there's the correlation between capital gain and capital loss probably not. There's a capital gain here and capital loss. It's probably not real, right? Okay. It's only negative 0.03. I do have examples about this parallelogram. Unfortunately, it's in note 14.r. I didn't put it up yet, so maybe I should just put it up. You can see that running this example. Okay, so that's about the. Well, this is intended to be only a partial solution. I actually didn't get it. I didn't do other stuff. I think most of you have already done univariate descriptive statistics along with like mosaic plus or bivariate like summary statistics by classes, right? So you've already done that. And we should continue with our class notes. Where are we at? Note 10, isn't it?
We did all that. Note 11, maybe. Note 11, maybe.
We done? We have not finished this yet, did we? I thought we had this line. Subsection 4. Not even that yet. So we probably some of these dots. I forgot which one. We already done this, right? About next time. We already talked about that. Class assignment, majority vote. Okay. And then you have this misclassification course considered. Okay. Here this course of misclassifying a class J as from class I is given by that function. Okay. And as the estimate expected misclassification cost for a node, okay, to be classified as class I is just given by this. Okay. And of course, the classification rule is then seek to minimize this result, right? We use what was that we talking about? To minimize the cost, okay? Just try to find one that will minimize the cost. Probably you should go through this quickly. Let's just look at examples. This is like, actually we just try to get some idea about how the tree model works. Okay? Okay, now let's look at stopping rule. Okay. A simple stopping splitting rule by setting the threshold value. Okay. Remember, MI denote the goodness criteria. Okay. If you split a parent node down to the child nodes and with only very small gain, then of course then you stop there, right? So that MI this is the purity gain, right? If you gain only quite a little, so less than some threshold value, then because then I will stop splitting. Okay? So that's the idea of that. Okay? So we can talk about this without referring to the mathematical form anyway, but just have the idea about this splitting. Okay? And problem with this approach is that actually usually if you set this threshold value too low, then you just have too much splitting, and tree becomes so large and so complicated. You have very complicated model, and usually it's overfitting, right? Too many parameters. Okay? And if you set threshold too high, then stop splitting too soon, and we could have underfit result. Okay? I want to see this kind of reversal that could occur. Could have something like this. Okay? So basically, usually people prefer to grow a tree first and then just cut a tree or prune the trees. Okay, that's certain according to certain pruning trees criteria. Maybe we should see example in action rather than just talk about this. Okay. But at the time we talk about this plotting the tree, I will see this tree model in action is much easier. Let's look at this section here. And by the way, this R part, okay, recursive partition, this package comes with a standard distribution. Okay? I forgot to mention that. And actually, I actually reinstall this package in my local library. It's not necessary. Okay? I wanted to remove that. Okay? But this anyway in the standard distribution, but not in the earlier release. That's why I still kept that. Okay? Because every time, I still remember I started from version 12. Every time I download a new release, I just update the package that I already downloaded before without reorganizing the package. So it's still there. Okay? But this is supposed to come with a standard distribution. Okay? It's in the installation. If you ever wonder that it's in we go to this one. Total program files, here it is in there. Look at the R folder. I still have the older version. I probably need to remove that. Forgot to do that. And then here under the R home, you can see the library there. And R part is right here. So it comes with a standard distribution. So you can see that. Okay. So you don't need to install these packages. Okay. It's in the standard distribution. Okay. It's just R part, the recursive partition function. Okay. And it's a model based. So here we do species model against all other variables. That is the case. Okay. And data is arrays and method is classification. Okay. This function is generic. Okay. You can do this in a regression tree as well. You can do this in Poisson regression as well. Survival modeling. Okay. So it's kind of a generic function. For our case here, we use a classification. Okay. So all we have to do is just run this recursive partition, and maybe you want to store the result. And further, we can extract information from this tree model, for example, by a trade representation of this result. Yeah, I changed a little bit. This is not really in a distribution. Actually, let me run this first, okay, without that. Okay. This is what you see in the. I forgot to update that. Okay, this is in the. First of all, you're going to see this. Okay, without labelings, it won't occur. So we need to do labelings of this result. Okay, so it's right here, right in the next one. Okay, next command do text. Okay. We'll show the result. Okay, with the tree model. And by default, something will be cut off. Okay. I'm going to modify this actually. I shouldn't have done that. Usually, it's a bad idea to use this command here. XPD equal NME that you turn the clipping off. Usually, it will just when R plot your graphical elements, you only plot within the window. Everything fall outside window will be clipped, so you won't see that. That's why. See, you see this result. Okay. Actually, at the moment, I didn't turn the clipping off, but there's a way to just do that. Okay. Actually, I need to rerun this one. Okay. So let's rerun this with, and now add this two in. Okay. Whoops. Where are we? Add one more line. So here we have this tree model, okay, with a different view, and then here we have this result. Okay, model this result. So I didn't leave enough margin, that's why it's still cut off. You can well, maybe you just try to set in the future, just set enough margins for that. Okay. I forgot to do that. Maybe 2 will be good enough. Okay. I think they should figure this out automatically. I don't know why they bother the user of this. So now it's not, the clipping does not occur here. And by default, the parents node will not be marked with like this classification. Read node information, how they were split. You can also, let me run this again. And then the text. Here you say all equal to is to mark all the nodes, including the parents' nodes. Okay? Probably it's better if you have see this tree model in action, so you can see that. So you can see that this tree model first originally was 50-50-50, right? Okay, and split at this criteria payload length less than 2.45, okay, it goes here, and payload length greater than or equal to 2.45 goes the other side, right? Okay. The other presentation is just show the conditional set on that. Okay, that's the default view of that. Okay? So we like this way. This is another way of presenting this result. Okay? And each node, if this is terminal nodes, it will use as rectangles. Otherwise, use a certain like an ellipse. Okay? So you can see that at the first split, you have 50, 0, 0 on the left child, and then 0, 50, 50 on the right child. Right? And then here, further split according to this criteria, payload width less than 1.75. Okay? And with this versicolor, this kind of split. In fact, later on we can see. Let's just see the report first, and then we just run a different view of this result. Okay? You can print the result. Just type the model itself. Okay. It shows that this is way too small. Huh? A terminal node will be masked with asterisk. Okay. So here, this is root node to start with. Okay. And for that, the split is done by this Setosa here. So here we have 150 in total, and 100 is the other one, the Setosa. And then this is a child node, right? Okay. So this is just a purely just Setosa, okay? And with the splitting criteria is given here, and we have other information as well. So they report something else. Let's see if I run summary. This is a summary of the tree model. It's more informative and takes more reading. You run a summary, so it tells you about the formula that come out with this result. Okay, and this x error and x standard deviation, these are cross validated. Okay, error and standard deviation. Okay. Cross validated error. Do a cross validation. We talk more about that. Okay. The CP criteria is also in our class note. About that. Okay. And node 1, 150 observation complexity. Well, there are some other splitting criteria. Okay. And pretty class would be Setosa. And expected loss about this. Okay. And class counts 50, 50, 50. This would be the pilots, right? Okay. And left side, this is node number 2. Node number 2 will be left child number. Okay. 50 observation, right node, okay, right child nodes from that parent is 100 observation. Okay. Actually, that shows you some information here. Okay. There are some primary splits. It's only that payload length was the first to be chosen. Okay. Actually, you can see that there's some kind of competitive one as well. This payload width less than 0.8. Okay. To the left, improvement will be sort of identical to the first one. It just happened in our formula we specify that. We specify payload length first, isn't it? Well, not in this one, but we see that at this we can see payload length appear first, followed by payload width. That's why that right order. Of course, that gives you some hint that you can actually see the different split later. And at the very beginning of this, for this lecture about this recursive tree, I talked about a classification with these two variables, only payload width and payload length. With this classified result, you can see there. This is another partition, like partition matrix, and you can plot the result. Okay? Let me just do everything. this is a part we have seen earlier, right? Isn't it? In our class note. Okay. It's produced by in this package, this KLAR, okay, with this partition matrix, okay, function, which actually is a graphical function. Okay, we produce something like that. Okay. You can try this out. You reverse the order. See what happens. Okay. Did I do this? Well, I actually did that in here, so maybe we can just take a look at that. Okay. So here I have pedal width plus pedal length, and here pedal length plus pedal width. You can see the results. Slightly different. Let me show you the second one here. And then we're done with that partition matrix. Okay. You can see curiously that with this criteria, okay, the tree was first split according to pedal width, either less than or equal to 0.8 or greater, right? That's the first split. And the same variable occurred for the remaining parts, okay? For remaining of observation, still these variables still win the result. They have the same improvement, so that's why this comes first, okay? Because here we space by this variable first. So here the split occur again.
It looks like you could have split among pedal lengths first.
Yeah, we can also
you did.
Yeah, it's possible. Okay. Not much so. The pedal width is probably better. Yeah, if you split this way, you probably if you split this way, you probably end up with more misclassified identities. And this is called partition plot. Okay. Now. Back to where are we at? There's something I didn't actually explain margins. I leave more margins for plotting the text. So here next time explain that. Probably what I need is 2, not 0.2, not 0.1. So I'll change that. And branches by default, branches is 1, meaning that without that, actually we can just use 1, okay, and see the result. Okay. Just do that. Maybe just do a default. Okay? Maybe still do 0.3 there and then do a default with this margin. Okay. So then we kind of comment this out, right? We steal this out. This is plot data, and then we do this result. Okay. Oh, I forgot to use the all equal to again. Here this is. The default view would be this sort of square types of the trees, okay? And the default is branch equal, I think the default branch equal 1, so they would this kind of square. You can specify any number between 0 and 1, so like that. And anyway, let you explain from that. It's kind of interesting because this add all equal to there. Space by 0. Okay. So 0 means that the default is 1, branch is 1. Okay, default 1 means you kind of have this square trees, you like it, and that way. And compress, like make it more the figures more compacted, so it's much easier to show. Okay. This graphics. Okay. Where are we at? Let me put these two in one. See, remember now we don't have to use a clipping. So let me just turn this off. Okay. Huh? Yes.
Just a quick question. You were talking about the order of which these things were done. Is it possible to end up with different results in the final?
Could be.
The final based on the order in which you split.
And of course, after that, then you can always vary which one gives a better result.
So not only is predicting the variables, but the order in which.
Or yeah, the order split also. See, the reason is that originally you can see that they end up with the same improvement. That's why you can choose one among the other, right? You can choose one against the other. So, and I just use, or this package just choose the convenient one, whichever variable appears first. Just use that. This I want to put this in like a two-panel graphic so we can see the difference. Here, this RP2 is this RPA with this model, and then remember, say we need to add a margin to that, right? Now we know 0.2 will be good enough, isn't it? So add a margin to that, okay? And here add a margin. So then you don't have to do this, turn off the clipping. So usually it's not really good idea to turn off clipping because then all the graphics element can be extended beyond that, and we have straight line like stretching outside. So it's not really nice picture. Okay, so let me run this two comments here. Let's do all equal true as well. Do we need a fancy thing too? Don't have to do that, right? Don't need to do fancy printing. So anyway, we have this result, okay? So here's in the graph. Oh, I forgot to run PAR. Forgot to run PAR first. The one that just flash out. Okay. Oops. Too compact. Huh? So the margin 0.2 is still not enough. Anyway, so you can see the splitting, you have this information, and you can see that the splitting is different. Okay. For this model, is the split at the pedal equals 0.8. Okay, it's Setosa and again, still pedal width, right? See, that's the one we have seen earlier. Okay, still split at the same variable, but this is the one that we see from our class note. Okay. First split at the pedal length less than 2.45, and then split at the pedal width less than 1.75. Now this one summary, and actually I didn't finish interpreting this result. Okay. Just take this for example. So there you can see they give you this primary split. So they are equal improvements. The first one, the pedal width is used. Okay. For this model, pedal width 0.8. And surrogate split. The reason that this is there because, of course, in our data set, we don't have any missing value. What happened? Okay, if the current data come in with missing value for that split variable, are you going to assign that individual to left child or right child? So in fact, basically, the idea of this is they do some kind of imputation, right? If you have missing value, they use. Instead of using that, of course, if you for current variable, this splitting variables is missing. So there's no way you can tell whether it's on the left child or right child, right? When you split that, okay? So they use the so-called surrogate split, and usually surrogate split occurs on the other one. So you can see that, of course, naturally, the pedal length less than 2.45 would be the natural surrogate split for that. So if pedal width is missing, then you look at this surrogate split and see if the pedal length is not missing. Okay. Do the split. So basically, this surrogate split working behind the scene, sometimes this could occur. Okay. So this is how it deals with this missing bit. Now, of course, there are cases when both are missing. There'll be further detail about algorithm, but this is the basic idea. And sometimes you can see in some example, of course, here we only got two variables here. Okay. Sometimes you see more than one surrogate splits here. If the first is not applied, then the second will be applied. Okay. Until finding a non-missing value in like different measurement, they can do the split. Okay. So splitting is what occurs behind that. Okay. So then you can. So we'll just assume that, say, for our current observation, okay, a new observation, in your data, this observation coming in with missing petal width. Okay, so of course this cannot be applied, right? If you look at this, so okay, split. Look at petal length instead, and find that petal length is less than 2.45. We'll assign this individual to the left child. Otherwise, we'll assign that to the right child. So that's one. Does that make sense? Okay. So that's how the split occurs. Okay? We can also look at another example, and then here we have note to. Okay. We can see that the summary is just too much information there, but actually it will detail all the when this split occurs. Okay? So detail at each nodes and about what kind of criteria was used and number, the cross counts and the posterior probabilities that's given. Okay. Okay. So anyway, that's about the going the tree. And here, this is how I plot that function. So I'll skip that and let you read that. Okay. You can plot this 3 functions anyway. Okay. Anyway, let me just run all of them. Okay. Okay. See that. Okay. So here, this is. Whoops! I forgot to turn off that parameter again. It's multiple figures again, so that's okay. Here, plug in this function. Should be easy. So this gives that the plot for this. Okay. And use just a plot function. Use like different results. Okay. And let's look at this iris data. So actually, I run one at a time. This is a view of that scatter plot. So scatter plot metric using this party map again, partition matrix. You can see that the split. Well, of course, here this is on the bivariate variables. Okay, the split on bivariate, just 2 variables at a time. Okay. And you can see each result. I do this here. Yeah, I don't have to repeat this. You've already seen that. Okay. So we see how we do this in the tennis data. Very interesting. Look at it. Okay. So let's just run it and see the result. Okay. So here, this is partition of that data. And then we mark this. Okay. Actually, it's really hard to read this outcome at first, okay? Because you have more than 2 levels, basically. Okay, the tree only mark them as A, B, C, D, E, and so on. So A stands for first level for that variable. Okay. So here, first way is at outlook because it's binary tree, and we didn't do three-way split. Okay. So binary tree, if outlook equal BC, then go down to this. BC stands for what? You have to go back and check with that. You have to know exactly what that is. Okay? So actually, level 1 is level A. Well, just a level A. Level A is overcast. Level B is rain. Level C is sunny. So actually, what this does is that weather outlook is either rain or sunny, right? If it is true, then go to the left chart. If it is false, right? Okay. This is use yes or no. Sorry. Or they label the other way around. So, okay. Because the first bit, because this is nominal, so first bit occur at just level A. Sorry. Okay. So basically, this is outlook equal A. This is kind of counterintuitive, right? Okay. Because at the very beginning, when I introduced tree model, we say yes, go to the left, right? So basically, here we are testing whether it's overcast. Yes, go to the left. And here, basically, the label here is saying the other way, right? If outlook is in B or C, then yes, go down there. Okay, and if no, go to this one. And humidity equal A. So again, you have to go back to see what level A is about humidity. Unfortunately, so this is not really informative. Okay. So humidity high and normal. Because unless you, otherwise you here is label, you put some legend here indicating level A for outlook is what. So we'll explain this things out. Okay. Let me start now. So I think it's probably better we see examples rather than just go into a lot of detail. Okay. But still, I'd like to explain a little bit about the tree model. Right?